Well, I have three different playlists. One of them is CRF, Conditional Random Field. The other one is Hidden Markov Model. And the other one is Maximum Entropy Markov Model. So HMM is a generative model. It's very complicated. That's why there are alternative methods that are discriminative, such as CRF. And this is a log linear model. The denominator, this Z, sums over all possible output assignments. So it's huge. So the computational complexity is huge. So that's why we should reduce it. We should create some creative, recursive, and dynamic programming approaches to deal with these. So even in inference, like HMM, we use dynamic programming. And so CRF is a discriminative model. Let's consider the same part of speech tagging problem. For a conditional random field, we need to define some feature functions first. Then, using our training examples, we estimate the weights of each function for each word. For example, the first feature could be the word ends with ing and it's noun. The second feature could be the word is a second word and it's verb. The third feature could be the previous word is a verb and the current word is a noun. So you see there are lots of ways you can create these features. Let me compare HMM to CRF. As I said, HMM is generative, but CRF is discriminative. And CRF is gradient-based, but HMM maximum likelihood estimation by counting, so it's easy, just counting. But the computation for CRF is harder in comparison to HMM, but it has great, strong performance. The graph in CRF is undirected, but the graph in HMM is directed. The context is global, that's why it doesn't have any problem of label bias that I explained in my playlist for maximum entropy Markov model. It doesn't have that problem because the context is global. And CRF are computationally more challenging. The reason is that normalization factor, the term on the denominator, is intractable. Like many things in machine learning, the denominator is intractable. And its exact computation is impossible or hard to do. CRF is a special case of Markov random field. So fundamental to many applications is the ability to predict multiple variables that depend on each other. For example, classifying regions of an image, estimating the score in a game of Go, segmenting genes in a strand. This is really beautiful application in bioinformatics. And extracting syntax from a natural language text. So all of them are called structured prediction because it's not just simple classification, but you should also respect the graphical model because that's the way the information is structured. And traditionally, this is the first article for conditional random field invented by these amazing scholars. So CRF is discriminative. I have a playlist for maximum entropy Markov model. I have a playlist for conditional random field. I have a playlist for hidden Markov model, but I don't have a playlist for naive Bayes because it's very easy. And it is a joint. We have either discriminative or we learn jointly. So it is either generative or discriminative. So CRF is discriminative. Maximum entropy model is discussed in more detail in this lecture because it's fundamental to the conditional random field. You understand conditional random field much better if you first start with maximum entropy. And the principle of maximum entropy is very simple. It says that if incomplete information about a probability is available, the only unbiased assumption that can be made is distribution, which is uniform as possible. And this allows us to be uniform as possible. Don't create any other bias. Let's be simple as possible. So the basic idea is to find a model, what is the probability of y given x, which on the one hand has the largest possible conditional entropy. This is conditional entropy, but is on the other hand still consistent with the information from the training material. The objective function later referred to as a primal problem. So what is the maximum entropy model? First, the training material here define binary valued function, those fi that I explained. For example, these featured here are binary. For example, 1 if y is name and x is Mr. and 0 otherwise. So if you have seen my playlist for lasso, those sparsity, you see most of the time it's 0 and sometimes we have 1. So it's very sparse. So it has some interesting patterns. The expected value of each fi is estimated. So we want to estimate the expected value of your features. Because you have an empirical distribution p tilde, so why not calculating e tilde f? And we know that if it is empirical, it can be written as this, the Monte Carlo approximation. And the maximum entropy model, so we have this, but because we have this approximation, we can write an expectation of your features as this. So in the primal model, that means that for each fi, its expected value on the primal, on the empirical distribution must be equal to its expected value on the particular model distribution. So these are M constraints. So we should satisfy these constraints. Also, we know the probability should be positive, the sum of them should be 1, and so on. So what do we do when we have constraint optimization? Well, if you have seen my playlist on optimization, you will notice that we can use this Lagrangian formulation, and these are Lagrange multipliers. And then so this is a first constraint, this is another constraint. We have M constraint of them because we have M features. So we have M constraints. So this is another constraint. So M plus 1 constraint. And the primal problem that I explained. And we can approximate it like this. So I assume that you have solved this optimization problem, taking derivatives, solving, and finally you will see that the answer is this. The answer is this. And the denominator is this normalization constant, or some people in physics call partition unity. A partition function is here. So as you see that it's a log linear form. It has a log linear form. The denominator is a challenge. It takes a long time to calculate that. It's huge. And so let's talk about directed graphical model. So, in naive Bayes, we have directed, but it is just for one of them, for one y. And this is the factor graph, if you're familiar with probabilistic graphical models. I mean, the book of Bishop in 2008, I guess, is great for if you want to know the basic things in graphical models and basic machine learning. And this is the independency graph for hidden Markov model and factor graph for hidden Markov model. You see, in hidden Markov model, the direction is from these hidden states to the observation state. But in the maximum entropy Markov model, it is the opposite. And in the CRF, there is no direction. It's undirected. So a probability distribution can be represented by an undirected graphical model using a product of non-negative functions of maximal clicks of G. The factorization is performed in a way that conditionally independent nodes do not appear within the same factor. It reminds me causality and those things that I've explained I explained it 2 years ago. Those causality, those graphical models, clicks, and those things. So these psi, historically we call it potentials. It comes from many different branches such as physics. And so it's multiplication of all of these things. And so it's Markov blanket, each of them. If you're familiar with the terminology of Markov blanket, then you understand what I'm talking about. So this is the normalization factor. Why am I repeating this so many times? So this is the maximum entropy classifier. And so now at slide 22, I want to start with conditional random field. This is a linear chain conditional random field because you see linearly wise your hidden states are connected to each other. For example, there is no jump here. Of course, that model is called skip model, and that's another form of conditional random field. But this is linear chain random field. So it's multiplication of your potentials, if you remember, over clicks, because you have many clicks. For example, this one and this one, you see you have many clicks you can create depending on your architecture. And the normalization factor is here. So the factor graph looks like this. This is the linear special form of CRF, as I said. And it has independency graph like this. And this is a sequence of length n. Here is length n. Because we have a sentence, a sum of words, these words, so the number of words is n. And M is number of features, because you know that feature matrix Fi, we have M of these features Fi. And we want to know what is lambda I. We want to learn this. So in the next lecture, I will talk about training and inference. And these are great scholars, amazing scholars. And for example, Hugo teaches machine learning and everything very beautifully. On YouTube, you can watch his lectures. 100 times better than my lectures, 100 times better. And these are very nice papers. Neural CRF parsing. I will explain this article. This is really important. What else? And this is, I've used, I think, some of the ideas in this article. And Gibbs sampling, because conditional random field, you can use Markov chain Monte Carlo. Markov. Some people say MCMC does not scale, but I think you can scale it in a beautiful way. And also you can use Gibbs sampling, Importance sampling. Everything you know in computational statistics, now you can use in conditional random field, and anything that requires you to calculate a complex denominator, that Z, that normalization constant, that people call it partition functions, that is a major obstacle in machine learning. And that's it.